Welcome to PADT, Phoenix Analysis and Design Technologies, where we make innovation work through simulation, product development, and rapid prototyping. As an ANSYS certified channel partner, we sell and support the full suite of ANSYS tools in the Southwest United States across 6 states. Our headquarters is in Tempe, Arizona, and we have offices near Salt Lake City, Utah, Los Angeles, California, Denver, Colorado, and Albuquerque, New Mexico. In addition, we provide training, mentoring, and simulation consulting with these ANSYS tools worldwide.
Hi, this is Doug Oatis with Phoenix Analysis and Design Technologies. I'll be doing 2 quick examples to illustrate contact and joints in a mechanical model to simulate interactions in an assembly. So in this empty project, I've already imported 2 different geometries. So this first geometry represents an actuator assembly. The second geometry is actually a bolted flange. So for the first analysis, I'll be doing a transient structural off of my actuator assembly. So I drag and drop my transient structural onto the geometry. This establishes a link to import that geometry into a new mechanical session. If you're not familiar with mechanical, this is where I'm going to assign material properties, define mesh controls, apply my boundary conditions, and do all my post-processing. So once my geometry is imported, mechanical will automatically have tried to define contact between each and every part in my assembly. And so this is a surface-to-surface based interaction. So if I wanted to, I could simulate a pin interface by specifying that this is a frictionless interface. But in order to do that, you have to clean up the mesh a little bit just to make sure that when you actually mesh this, you have a cylindrical surface rather than a highly discretized interface. And so if I'm just looking at the motion of this assembly, what I can do is utilize joints. So I'll go ahead and suppress this auto-generated contact. I will go ahead and insert a new connection group and just specify that rather than creating contact, I want to go ahead and create joints. And so I can then right mouse click and tell mechanical to go ahead and automatically detect joints. So mechanical is going to go through the model and look for certain faces or features that it considers joint worthy. And so typically that's going to be cylindrical faces that mate up, or it's going to be planar faces that are together. And so mechanical is going to do an okay job most of the time. Typically with joints, you're going to have to do a little bit of manual work. So I can see that for this first interface, mechanical did a pretty good job of figuring out that this is a revolute joint. Mechanical shows me which degree of freedom is open, and so it has rotation about Z here, which makes sense because I want this to be able to spin about that pin. So I look at the other 2 and I can see that mechanical picked up on the fillets that kind of stack up nice and close together, but it's not quite what I want, so I'll go ahead and suppress this. And then the last joint is a fixed, where it assumes that it's trying to bond these 2 faces together. Again, valiant effort, but not quite what I wanted. So I'll go ahead and just start building my linkage. And so for this face, I want to ground this out, and so I'll specify that this is a body to ground joint, specify that it's a revolute joint. And I can see that it automatically assigned a coordinate system where the Z-axis is along the axis of that cylinder. I can click the configure button up here and start playing around with that, and I can see that because I have this other joint already defined, my arm already goes along for the ride. And so just keep on building up this assembly. And so I have this properly defined. I have this revolute joint properly defined, so I'll just work my way to here. I'll pick these 2 faces, go back, specify this is a body-to-body interaction, so I'll specify that this is a revolute. And if I want to, I can go back and clean up or add this additional face. So if I click on my mobile side, if I click that, go back, hold Control, left mouse click on that other face, and then hit apply. I've now included all of the faces in this clevis joint. So I can go back, check on my interactions. So if I click on configure here, I should be able to see that the entire arm now goes along for the ride. So slowly but surely. Next, I basically want this arm to slide back and forth, and so I'm just going to ground out this block. So do body to ground and fixed. And so you can see that there's no open degree of freedom here, so this is just completely grounded out. And lastly, we'll do a translational joint between this face and I'll use the selection pane to pick on the bottom face of this body. So I'll do body to body. This is translational. And we can see that in a translational joint, the X direction is the open degree of freedom. And we can see that as it's oriented, that's not quite right. So I can easily fix that by expanding this translational joint. Click on the coordinate system and just come down here and specify that X doesn't point that way, X should point this way. And so now I can double check that everything is properly connected by going back to my, this is what I'll be driving it from. Click the configure button, and what I should see is I just should have a slider mechanism. So everything looks nice and neat to me. As far as showing an interesting simulation, I'll go ahead and create a spring that's attached to this and is grounded out somewhere over here. So to simplify that, I can select this face, right mouse click and say create a coordinate system. And so next I'll go in and I'll select this face, do a body to ground, and then scroll down to spring. So I'll just specify a dummy stiffness. And then the grounded out edge is going to be the reference side, and so I'll just use the last coordinate system. This is the one that I had just created, and then I can see that X is this direction, and so I'm just going to make this spring 20 inches long. So it's as easy as that. And so now, instead of having all of my interactions defined by a surface-to-surface relationship through contacts, I'm using joints, which essentially linearizes the interface. So if I wanted to apply boundary conditions here, I don't have to really apply any fixed supports or anything, because this is already grounded out, this is grounded out, and my spring is grounded out just by the way that they're defined in the connections group. And so if I wanted to apply some type of torque or just a known rotation, I can just drag and drop this revolute joint into my simulation. And then I specify what type of load I want to apply. Do I want to apply rotation, rotational velocity, acceleration, or a moment? And then I'll just specify the magnitude. The reason I have a question mark on my analysis settings is that I haven't specified my time step controls. So if this is a 5-second simulation and I want to work in my, whatever type of time stepping criteria, I can do that. And then I can specify I want to ramp from 0 degrees to 45 degrees. And so that's all I need to do in order to set up my solution. And so when I can go ahead and click solve, I'm going to do a bit of a cooking show and switch to an already solved model. And so I can see my deformed solution. I can animate this however I want, and I can see that my spring is compressing as my wheel is rotating. If I wanted to look at stresses on particular parts, I could select a part, insert a stress result. We can see that my time stepping may have been a little bit aggressive, and so there was a little bit of a startup bouncingness to my results. I can go ahead and see that. If I wanted to look at results at any one of my joints, so let's say I wanted to know the total force acting on this pin, I could drag and drop this onto my solution branch. I could evaluate all the results, and I could see the forces, or if I wanted to, I could switch this to be moments, look at rotations, pretty much anything you wanted to look at on a joint. So fairly straightforward in order to use joints to define the interaction. And again, I'm not actually solving any surface-to-surface contact. This is more of just defining relationships between surfaces. Alright, so returning to my project page, I can see the actuator assembly that I just set up to solve the transient structural. There I'm going to go ahead and establish a static structural environment. I'm pointing to my bolted flange example. And so again, by double clicking and establishing these links, all I'm doing is telling my mechanical model where to pull geometry from. And so as that gets imported into mechanical, again, mechanical, this is where materials are assigned, mesh is defined, and contact or joints are defined, boundary conditions and post-processing occurs. So as I can see, mechanical already went through and did its best to define contact between each and every body based off of surface proximities to each other. And so I can see that going through all of these, I can see each and every bolt should have contact defined. But I've actually gone through and modified the geometry a bit just to illustrate some issues that may happen during an assembly simulation. And so I went through and essentially broke these beams and pulled the head of them up a bit higher. So if I highlight these two faces, I can say, show me contact that is defined between those two. And I can see that automatically contact was not generated between this bolt, dummy bolt, and this flange. And so I can do the same thing for here. So I can go to contacts common to, and I don't see anything. So what I can do is, the way that the contact or joints work is that it's looking for faces that are within a certain offset of one another. And for this, it's using a value of very small value compared to the overall assembly value. So what I can do is, rather than manually going through and defining them, I can essentially create another connection group. This is responsible for building automatically defining contact. And what I can do is I can actually measure the distance between my two faces. So again, using the section panes, I can select those two faces, look at some information here, and see that the distance between these in the Y direction is 0.024. And so what I can do is, right here, I can see that that value is wrong. So rather than using a slider method, I can specify this. If I just put in a very large number that's larger than the offset, and if I move my mouse over, you'll see a bullseye that represents the distance between two surfaces that it's going to look for contact. If I right mouse click and say create automatic connections, I can see that it does an okay job of building up contact. And so, because the gap between the bottom of the bolt head and the flange is larger than the radial gap between the two, I'll just go ahead and clean up my contact, because I don't want bonded contact between my the bolt shaft and the through hole. So if I click on target, hold down control, left mouse click, which unselects, and then hit apply. Do the exact same thing over here. Hit apply. And so there I go. So I now have, this is a way of simulating or repairing an assembly that has kind of sloppy geometry in certain regions, but very clean geometry in others, and that I can tell mechanical to search for a larger offset between different faces or different bodies. And so what I want to do is first specify that the contact that was automatically defined between these two is frictional. And so I'll say contact common to. And so there are multiple ways that you can simulate contact, or multiple behaviors. So by default, everything is bonded. We're essentially welding or gluing everything together. And so I'm going to go ahead and specify that I want this to be a frictional interface, type in my own value for friction, and there I go. So next I'm going to actually do a bolt preload for all of these guys. And so I'm going to kind of show a trick for that. So I'm going to hide this guy. I'm going to look at the side. If you right mouse click, hold, and then left mouse click, you can see the cursor changes to be a box select. So I'm going to draw a box going from right to left that selects all of those faces. I can then hit the letter N, which creates a name selection. I'll just type in my whatever name I want to give it. So this is now just a group of faces. And I'll show how those come into play later. So again, hold right mouse click down, left mouse click. I'm now back into single selection. So I select this face. I'm just going to fix this guy. I'm going to apply a bolt pretension to one of my bolts. And so go up to loads, bolt pretension, specify. These are all dummy numbers, so it doesn't matter. So now, rather than going through one by one applying that bolt preload to each each and every cylindrical face, I'm going to go and use this object generator. So I click on this, specify, basically I have my bolt pretension highlighted, specify that I want to repeat that over all the objects in the bolt faces. And so again, this was applied to a cylindrical face. Bolt faces is a group of cylindrical faces. So now when I click generate, I can now see that it applied all of my bolt pretensions for me. And so now if I wanted to play around with, you know, leaving one or more of these open, so bolt pretension, so let's say, you know, I actually want to play around with a tightening sequence. And so I can change this to be open, meaning that basically this won't accept any type of axial load. I've basically broken the nut loose, and so it's free to do whatever it wants. And I'll go ahead and open this guy as well. And so there I go. And the last thing you may want to do on this is, so on this frictional interface, what I can do is actually apply contact sizing to it. And so one way that you could do that is to drag and drop contact sizing here. And so this is a way to define sizing specifically to the faces that are involved in a contact interface. But for this, I'm just going to apply a mesh control to the face, just to one side of this. So I'm going to hide all the other bodies, apply sizing here, and then I can type in my own size, and then you can see the bullseye representation of what that element edge length is going to be. So that might be a little too small, so that's a little bit better. So now when I generate my mesh, the only reason I'm doing this is because this is a nonlinear interface, so I want to make sure I have enough contact detection points in order to properly evaluate what's going on at this flange. And so after that, I'm just about ready to solve. And so this simulation, you know, if I wanted to, I could add an additional step to it in order to first cinch down all of my bolts and lock them down, and then apply external load, and then track what happens with my bolt or my flange for that. So again, I'm going to do a bit of a cooking show and switch to here. So I have two environments that I've already solved for. And so this first one is going to be exactly the same, and so as what I just showed you, except I've already solved it. And so for this, you can see that some of the bolts are open, some of them are closed. If I click on my top level, I can see which one of these are open or closed. If I don't like how it's shaded, again, I can, you know, randomize the coloring scheme. But now I can come down here, and so if I wanted to look at just the information on that frictional contact, I can go ahead and insert a contact tool. I've already done it here, but I'll repeat it. By default, it's going to be looking at all of my contact pairs. I can click in this upper box that unchecks it, and then I can just click this one box and specify that I want to look at the status, I want to look at the and the pressure. And so the status is just going to show me, and so we can see here that this actually isn't the best bolted flange. And if we look at a cross section of this, we can see why, and that the bolts are actually over here, so it's going to cause everything to pretty much just kind of cinch down on an edge. And so if this was my concept for sealing off some type of internal fluid or air, I can see just looking at my contact information that the number of bolts that I've defined and the way that I've simulated or defined where my sealing surface is in relation to the flange, this isn't going to work. So if I look at my contact status, it'll show me where it's sticking, where it's sliding, where it isn't touching. And so the difference between sticking and sliding is essentially just a comparison of the normal force and the coefficient of friction versus tangential force. And so I can see that, you know, in reality, this probably isn't the best way to seal a flange. And so it's good to know that's why we're running a simulation. If I wanted to look at, you know, the total force going through a contact pair, I could right mouse click on my contact pair, and I can copy it, come down to solution, and paste it here, and that automatically inserts a force reaction scope to that contact interface. And so now if I evaluate the results, I'll get to see, So the total force should essentially be the total bolt load that I've defined going through that flange. And so going back to my already pre-solved cooking show, I actually went through and using Space Claim, I modified the flange to actually be a bit beefier and actually have the bolts be in the middle of the flange. And so if I do a section plane, you can see that the flange is just much, again, much thicker, and the bolt actually goes through it and will actually act to cinch down properly on that. And so again, same bolt preload numbers, and again, these are dummy numbers, they don't represent anything, so obviously this isn't something that represents anything in reality. So now if I look at my contact status, I can see that I've properly cinched down around each bolt hole, but it looks like I actually need more bolts if I were to actually, if I were concerned about sealing off this cavity. And so again, looking at the contact pressure, I can see that. And so yeah, this gives me a good clue about how my structure will actually interact. So using the contact tool, I can see the results after my load has been applied. So one thing that I did not show initially was, so I went through and I have defined all of the contact. This is the original model and the repaired contact. Is I can actually look at what my contact is doing before any load has been applied. And so if you have parts that are moving, parts that should be touching, you can actually have the mechanical solver tell you, are you actually touching, or is there a gap, is there penetration? So that way you can troubleshoot why are you getting stresses between two parts, and it turns out that there's actually some type of interference that it's trying to resolve. Or if there are parts that are flying away, it's because they're not initially touching. So I can click on this and look at my initial information. You can sort based off of any of these columns, and so if I wanted to see what's open, what's closed, I can look and see that these two are currently far open. And so if I right mouse click and say go to selected items in the tree, I can see that these are actually considered open. And so again, that's because the gap is too big. So I can numerically close this just by increasing the pinball radius to be something reasonable, something bigger than the gap. So something that looks like that. And so I did this on the previous model before solving, because if I hadn't, essentially what would have happened is that there was no contact that would be enforced between the bolt head and this top flange. And so lastly, while I'm back in the connections branch, just to show that you can create contact between parts, so I showed these two methods that automatically define contact. And then I created this one, and then I went through and cleaned up the contact. If I just wanted to manually define contact between two parts, what I could do is use the contact drop down, and again, I can specify the behavior at the interface. So if I want to do bonded contact between this bolt and this flange, it's just as easy as that. And so you can use the body views just to make sure that everything's right. So you can manually create it, you can automatically have mechanical automatically create it, or you can clean up something that has been manually or automatically created. And so the nice thing is you can mix and match joints, contact, however you want in a model. I can use joints here in order to simulate the preload. I can specify a translational joint and then specify a joint load and then lock it. I can mix and match however I want. It doesn't have to be transient. It doesn't have to be static structural. It's just a way of interacting between two parts. So if you have any other questions and you're in PDT's territory, which is Arizona, New Mexico, Colorado, Utah, parts of Southern California, please give us a call. We'd be happy to help you. If not, contact your local support provider for additional information on using contact or joints in assembly simulation.
Thank you for watching this video. If you have any questions, you can jump on our website at padtinc.com or give us a call at 1-800-293-PADT or send us an email at support@padtinc.com.